share my slides. Let's see, share window slides. Great. So again, it's really great to be here. So I lead the Columbia Intelligent and Connected Systems Labs. One focus of our lab is looking at how to embed intelligence into these resource-constrained platforms. So things like mobile devices, wearable devices, and many of the challenges presented in this kind of platforms. The other driving kind of force is we tackle real-world applications, and we try to use technology to solve or improve in these applications. And health and fitness and wellness is a very large part of that. So today I'm going to talk about several projects in my lab that tackles health and wellness. So I like to start with this kind of overview slide. This is sort of putting many of our projects onto this one slide, and it's organized in this way where the x-axis represents the form factor. So for example, to the very left, to the top right part, let me use a pointer here. Error options, screenshot present lessons, error options. Okay, so to the very left of this, we have a project where we designed a custom integrated circuit that can compute the time difference of arrival between multiple channels of microphone. So this is something that's at the sub-millimeter scale. This chip is then used in several other projects looking at pedestrian safety, construction safety. But to the very right of this slide is a project where we use reinforcement learning, use a recommender system to provide recommendations to occupants in buildings and in cities on how to help the building reduce the energy consumption while preserving things like comfort and productivity. So that's a project at the kilometer or at the city scale. So as you can see, we have many projects spanning different scales. So I want to talk about three groups of projects here. So the first group of projects involves health, in this case, physical health. So this project here, which we're calling Privacy Pillbox, is our take on the smart pillbox. And our contribution in this project is a new way of detecting whether pills has been taken or not using optical sensors. We're also focusing on the privacy aspect of smart pillboxes, making sure that sensitive data such as medication is transmitted in a very secure and privacy-preserving way instead of to the cloud. We have a project that's focusing on something called a kangaroo mother care. This is the idea that for newborns, it's very important to have skin-to-skin contact between the mother and the child. And we are introducing a novel way of using conductive fabric to monitor the amount of time, as well as vital signs. So that's very important to especially premature babies. So that project was presented in Mobius 24 and received Best Paper Award. To the right of that, we have a project, and I named this project Dr. House. This is in collaboration with COHK. So this project is essentially trying to create Dr. House, right? If you watched the show, and we're looking at how to use large language models to be able to converse with patients, to be able to diagnose patients. And I think something that's very different in our take on this is we're also using up-to-date medical information, not only textbook medical information, but also data that's captured in this database called UpToDate. So that was presented at UBCOM. And on the bottom side of this, we have a project that's called AR stethoscope. So we're using augmented reality to enable everyone to use stethoscope as a tool for self-monitoring, especially for monitoring heart issues. So I'll talk about this project in more detail in the next couple minutes, in the rest of the talk. We also have a project called fever screening. So this is the idea that we can use a very inexpensive thermal imager, such as the FLIR thermal camera, to perform continuous multi-person fever screening at an accuracy that's higher than some of the $10,000 kind of devices. So that project came out from the COVID pandemic and some of the interesting technologies we introduced in that project. So I'll also talk about this in more detail later. The second group of projects that I want to share involves mental health, involves sort of the emotional side of things. So we have a platform, the glasses-based platform that allows us to monitor emotion, both apparent and also true emotion. We also have a what we call AI therapist. This is effectively trying to encode the expertise of therapists and utilizing large language models to enable home devices such as Alexa and Google Home to perform psychotherapies. We have a project which we call Social Mind. This is again in collaboration with CUHK, where we use AR glasses as a platform to provide real-time suggestions in a social setting. Think about, let's say, you are at a conference and you're trying to have a conversation with the keynote speaker, and you are sort of not sure what to say, right? So this AR glasses is able to figure out the context of the situation and also provide real-time suggestions on how to initiate conversations. We also have a project on AI mental status exam. So this is a mental status exam, or MSE, is a commonly used exam by a psychiatrist to assess the mental status of patients. And here we're trying to do this using AI and using technology as opposed to a human kind of direct interviewing kind of scenario. So finally, we have a couple of projects on fitness and wellness. To the very left, we have a project what we call Sweat Fabric. This is using conductive threads that's woven into clothing to assess the amount of sweating. So what distinguishes this project from other solutions is that it's a very comfortable way, right? There's no rigid electronics. People are able to wear our system without any discomfort because it's seamlessly integrated into the fabric of the t-shirt. We have a project on running metrics. This is essentially looking at how to use a non-invasive way and a very cheap, inexpensive way to tell runners important metrics such as cadence, ground contact time, so that it can improve their running performance. And finally, I will talk about a project which we call the RASP drone. So this is this vision that our lab has, which is in a few years, we will have this micro aerial vehicles, these tiny drones that flies around in the housing, in the home environment, and be able to do many interesting things. So with that, I'm going to dive into a couple of individual projects. And I apologize in advance that I will sort of cover some of these projects at a relatively high level. But if you have any questions, I'm happy to answer them after I cover these projects. So the first one I want to talk about is fever screening. So we're kind of just coming out of this COVID pandemic. And one thing that everyone is, I assume everyone is familiar with, is how many of the businesses require people to put their head in front of a thermal imager, right? And that's not a very effective way of performing fever screening. So we're looking at how to make this process inexpensive and also more accurate. So this is a photo of our system being deployed at Columbia Doctors, which is a medical center. So my student Peter here is actually doing the ground truth data collection. So you see here a nurse who is holding a traditional thermal, what do you call it, a temperature, right, to assess the temperature using this full head scanner. So this is the old way of doing things. And we're also doing this because we want to obtain ground truth to evaluate our system. But more importantly, right, the device on the right, which is mounted on this tripod, is what we have, and it's running the algorithms that allows continuous screening of multiple people. So what our device is able to produce is this thing on the right, which is as people walk in, it directly can tell the nurse that who has or has not fever or does not have fever. So like what I mentioned earlier, right? The current solution to this is either you have to stand in front of this thing, which makes it very slow to, if you have a large traffic of people, right? It takes a long time. At airports, you also see these commercial thermal scanners, and you have to line in a file and go through this one at a time. So for that, one, it's very expensive. And we also found that their accuracy is actually not that good either, contrary to what most people believe. So we're effectively trying to do what these commercial scanners can do, but in a much better way and lower, with lower cost. So to enable that, we have a couple of ideas. One is we have to do distance calibration because the inexpensive thermal imager does not calibrate distance as accurately as we can. We have to do this surface and medium calibration. So when there's a black body sort of radiating surface, such as the human skin, the inexpensive device does not distinguish between human skin versus any other objects. And also the medium here is air, so we calibrate against that. That gives us some increase in accuracy. But most importantly, and this is the part I want to perhaps dive into more depth, is our idea of effectively using multiple frames of the image to improve the accuracy. So think about this as similar to computational photography, right? You have, I guess, the Google Pixels that takes 10 images in succession and then overlay them to get rid of the noise. So it's very similar to that, but in our case, we have to create 3D point cloud model of every person's head and then transform each of the image and then overlay them. And finally, we also do something called thermal point mapping. So depending on the location on the head, the temperature is also different, even for the same person. So diving a little deeper into this whole how we are able to improve the accuracy by overlaying multiple images, right? Imagining as a person walks through the observation window, we capture 30 frames per second, right? And there are, obviously the person's moving. However, we can perform just simple geometric transformations, right? To transform kind of the images and overlay each of the images onto this 3D model of the head. And in doing so, we're able to reduce noise. We're able to improve the signal to noise ratio. So I'm going to skip a little bit of the transformation process, but obviously we have to match the RGB image with the thermal image. We have to perform geometric transformations. So the other part of this project is the systems aspect, right? How can we do this using a low-cost smartphone attached with a thermal imager? So the front end is a Flare 1 Pro. I think it's about $300. Attached to just a Nano. And this device is performing a little bit of local processing and then transmitting that processed image to our server. Within the server, we utilize this Redis in-memory database combined with the data processing pipeline that I described earlier. And overall, the server will then have this publish subscribe kind of model where clients, in this case, the hospitals that are using our service can log in through this interface. And we're using containers, Docker images, so that we can service multiple of these thermal imaging systems without having to worry about contamination between these data. So we performed the experiment over, I think, 10 months, and we scanned about 4,000 real patients. We are able to show that our accuracy is much lower than what the baseline, the state of art is. So one thing I want to emphasize is the figure on the left. This is the ROC curve. So what's really important about this application is that we want to make sure that we should not miss anyone who has fever. But it's okay if we have a few false positives, right? So ignoring most of these lines is just using different models. Looking at maybe the orange here, right? The one that's performing the best. So what this is saying that is we can have 100% true positive rate at something like a 22 or 23 false positive rate. So this is often the operating point that we have to work with for fever screening. The right is just one snapshot of a confusion matrix for I don't remember which model we used for this graph, but as you can see, it's doing fairly well. So again, we deployed this over 10 months with over 4,000 real patients. The figure here is showing that our average error is around, let's say, 0.4 degree Fahrenheit. And of course, it degrees over distance, but in most cases, we can have distance about 2 to 3 meters and still have acceptable error. We open sourced everything here, and we invite people to use our service. All right, so I'm going to quickly jump to a different project, again, within the physical health umbrella. So this next one is called AR stethoscope. I think the motivation here is hopefully fairly straightforward, right? So stethoscope is a tool that doctors are using for screening heart health, lungs, and a number of different things. But it's something that, while very cheap, it's not something it's not something that we can use because we don't have the medical expertise. So this project is aimed at exactly that, which is, can we do this? Can we enable people to use stethoscopes at home? So the idea here is we are essentially mimicking what doctors do in a clinical setting. What they would do is they would use their eyes to first perform visual inspection, right, where locating where to place the stethoscope depending on where the chest locations are. And we're using camera for that. Then the doctor will listen to the sound coming out of the stethoscope to do micro adjustments, right, to make sure that the location is optimal so that you have the best SNR. And we're using microphones that's embedded in the stethoscope. So a side note to this is for this project, we're primarily looking at heart murmurs. And what distinguishes a abnormal heart murmur is what distinguishes a normal heartbeat versus a murmur is that there's the S1 and S2, and then for a normal heartbeat, there is not a lot of energy in between. Whereas for a murmur, you can see a gradual decay, but not as clean as a normal heartbeat. So here is a quick, I guess, demo of our system. So the person will be sitting in front of his smartphone or computer monitor using our system. The display will show a heart kind of overlaid on top of this person's chest. The person can actually move around, and this overlay will move according to where the person is, and you can shift it around with no issue at all. And what's happening is that the person will then place the stethoscope onto where the AR indicator is. The system will then listen to what's being heard and then provide micro adjustments. So this is what do you call it? This is a speed up version of this. But if we slow down a little bit, you can actually see micro kind of adjustments around. See, So right after we got here, right, it's actually directing the person to move around a little bit, which provides kind of a scan of locations nearby that potentially provides better SNR. So I think that's a very nice kind of cyber-physical human system, right? We have the human feedback to provide better signals. Okay, so in the paper we talk about how we evaluate this with real test subjects, and people are able to actually use the stethoscope without prior medical knowledge and be able to tell their heart conditions. Now moving quickly onto kind of the next one. This is the idea that we have these drones, right? It will be great if in the near future we can have these reconfigurable drones that flies around in the home. And if we can combine that with AI, it can become a very useful platform for the home. And certainly for elderly homes where there are many tasks that a reconfigurable drone can help with. So this is the, in some sense, you can think of these drones as the arms and legs of AI agents, and they can adapt to diverse tasks and versatile applications on demand. So I'm going to kind of talk about the hardware side of things first. This whole system have several parts, right? Obviously, there's a drone, there's a landing station. So the drone can autonomously land itself so that it can swap the payload. The payload could be a sensor, could be an actuator. There's also a library of sensors that we have built, and we hope to open this up so that others can contribute to this repository of sensor modules and actuator modules. So this image up to the left is kind of an older version of this, but as a first prototype, it really it's able to show this proof of concept. So in terms of sort of the hardware layering, right, we have the mechanical layer, we have the electrical connection layer, we have the software layer, which provides things like dynamic driver loading, failure detection, local storage, and also the local kind of task execution side of things, and also path planning, how to plan the paths for the drone to fly. So mechanical layer, again, this is an older version, but it gets the point across, hopefully. We have this funnel-shaped landing station. This allows the drone to land without being as precise. So usually it's very difficult for a drone to land within millimeter kind of accuracy, right? So this physical kind of shape helps the drone to land. We have these gripper modules. It grips down the sensor module, and there's the conveyor belt, which is how the new modules will be loaded. We have these photoresistors, lasers to know exactly where the sensors are. In terms of connection layer, we designed it such that it exposes what we believe to be the right electrical connections. So there's the sensor side, there's the module side, and we're using these magnets that's embedded on the four corners as a way to securely attach a module with the drone. We experimented with a bunch of different ways, and I think this is the most optimal for what we need. In terms of interface, we expose I2C SPI, analog, UART, of course, power, among different things. In terms of the mechanical mechanism, right, we have this gripper thing. We also did force simulation to make sure that the cage that surrounds the sensor module can sustain the most amount of force. And as I mentioned earlier, we designed a bunch of different sensors, and we encourage more people to join this. So software layer, I kind of already described what it does. It allows us to load the right driver depending on what the sensor is attached. So putting everything together from the hardware perspective, what we are able to enable is that a drone coming in with a sensor A will autonomously land onto this landing station. We will autonomously, everything is autonomous, detach the sensor, conveyor belt will retrieve a new sensor, and then it will be reattached to the drone, and the drone will fly off to execute the next task. So at this point, I think we kind of took care of the mechanical side, the hardware side, and also the embedded software side. The next part is where, hey, what can we do to really make this drone useful? And really, it needs to be able to respond to human commands, right? And especially directly spoken commands. So this is where we create the next part of this project, which is the user can instruct the drone to perform certain tasks using natural language. The drone will translate that natural language-based task into machine executable commands. It will use the right sensor or the actuator, perform the task, and then come back and transmit whatever data that's needed for data analysis and then feedback to the user. What are some of the tasks that people can issue, right? Ideally, we want this to be anything that the user wants the drone to do, and the drone should be able to perform that task to the best of its ability, depending on what resources are available. And that's exactly what we're doing here. Some of the examples, right? We can ask the drone, where is the warmest place to sit, right? This is asking the drone to perform a survey of the space and then perform some data analysis and give me an answer. We can ask, is the stove still on, right? That's a very specific command to, let's say, go to where the stove is and see if the stove is on. We can issue a command such as monitor for someone falling, right? I think for many sort of aging population, one concern is falling, and the system can help with that. We can also use kind of actuation-based tasks, such as bring a snack to my pet. So the other side of this is first of all, we're using large language models to help us understand what the meaning of the sentence is. But we also use cameras that's embedded in the environment to understand the context, so what the actual environment looks like. So I guess we are dividing that into two parts. One is task comprehension, which is using LLM to understand the task. The other is scene understanding, which is using cameras and potentially other sensors to understand what the scene is. And here we use vision language models to do that. So putting all of that into our architecture, we start with the first phase, which is the user issues instruction. We have as input the camera that's embedded in the environment to provide us some context, and then we perform our task understanding and scene understanding. So let me dive into a little more detail on what we're doing here. So we have a user-issued natural language command. Where is, using this example, where is the warmest place to sit? Combined with a bird-eye camera shot of the overall space. So the next part is we formulate the prompt, and there's quite a bit of prompt engineering going on here. As most of you know, large language models are very sensitive to how you phrase the prompt. You know, through this process, we actually discovered many interesting things about this prompt engineering. So we start with, you know, this is input image. It's a top-down view taken from a camera installed on the ceiling. By the way, this is exactly the prompt template that we're using. I would like to know, and substituting what the command from the user is, in this case, where is the warmest place to sit, and which type of sensor should I use to better assist this task. I have list of sensor available, right? So this is the template. And then I also say that your response should be in the form of reason. So we don't really need this output, except that this helps the visual language model to reason about this in a more logical way. And target, right? What's the object of interest, and also the payload. Which sensor module should I pick up? So feeding that into VLM, we get something like this. The warmest place to sit can be determined by measuring the temperature at various seating areas. These seating areas influenced by blah, blah, blah. airflow from vents, positive direct sunlight. So this is all great, right? We don't care what this is, except that we can be sure that this is actually doing reasoning in a correct way. So by focusing on these seating areas, we can apply a clear picture, blah, blah, blah. But for us, for the system, it needs to know something, which is we're looking for objects, which are chairs, and it uses a temperature sensor. So given that, we have to then ask a second question, which is where exactly are the chairs? So for this, we're using these open set object detection model, which give us bounding boxes that allows us to send it to the drone to fly to. So at this point, I know exactly where I need to send the drone to, and I know which sensor to use, which allows us to then equip the drone with the appropriate sensor, as well as flying to wherever it needs to go and perform the task. So this is the task execution phase. So once the drone comes back from the path that it flew to, we then collect the data from this phase and then perform data analysis again using a large language model. So here we use a different prompt. So first of all, we feed in input data, right? This is essentially, these are the temperature sensors in this case. Sorry, temperature data. The prompt is, this is data from, we know which sensor it is, so it's temperature sensor, measured by drone task with, again, the original task, finding warmest place to sit. We have a bunch of other kind of suggestive things to really help the LM understand what we wanted to do. We say something like perform EDA to understand data, then perform necessary pre-processing, only answer in the form of answer, location ID, explanation, and analyze process. So in the plan explanation to user, try to add some numbers from analysis. Again, this is more art than engineering. We try to play around with the prompt template to make sure that the large language model can perform the best. So with that prompt, the large language model will generate the appropriate code to analyze the data, perform the data analysis, and finally output the answer. So right here, it says answer is 2. So again, this is the corresponds to this chair. Right? This is where the warmest place is. Explanation to user. Again, this is coercing the LM to think logically. The data from temperature sensor across 4 locations show that location 2 has the highest average temperature at 24.4 degrees. And it also says a bunch of other things that I don't really care about, but important for the LM to do things correctly. Analyze process says what it does. Right? Each CSV file was loaded, analyzed, calculate average temperature. The data was checked for basic statistics such as mean, max, standard deviation, etc., etc. So I hope this shows how our system is able to take as input a natural language-based command, perform all of the necessary execution autonomously, and finally return to the user an answer. So we performed a bunch of different tasks and evaluated against what the baseline is, right? Which is if the system does not have a drone and only rely on something like a camera. And we can see that for various tasks, find the phone, find the key, sit somewhere with certain criteria, check the state of object, performing surveillance. Obviously, with our system, we perform much better than without. All right, so I think this represents something that's more of improving the wellness potentially, but just simply making life much more enjoyable. Now I'm going to shift a little bit to fitness. Right? So this project called Running Metrics. This is where we provide information such as cadence, ground contact time, and balance. This project was actually started by a student, Jinping, who is a very enthusiastic with marathons, and she is trained as a certified running coach. So she's able to really understand the underlying sort of data that's important to professional runners as well as casual runners. And these metrics are important to help prevent injury, to monitor running performance, and improve running efficiency. So there are existing kind of solutions, right? You could use expensive motion capture such as Bicon. This is obviously not something everybody has access to. There are work on wearables, attaching these wearable devices to the leg. There is approach using millimeter wave radar. Again, these are not something. Well, first of all, either they're not something that you can easily instrument, requires potentially a lot of training phase, or it requires a wearable device that you have to wear. In the commercial space, there are a bunch of these wearable watches. You can also attach the smartphone to your arm to perform something similar. So they are either uncomfortable, right? People who run marathons, they don't want a big phone attached to them. They also don't want to wear something, right, that can produce skin irritations. So what we saw in the Columbia gym is that almost everyone has their smartphone placed on their treadmill. And that got us thinking, right? Can we simply use algorithms installed on a smartphone app to perform these kind of running metrics? Now, it turns out it's more challenging than one might expect, right? One, there are lots of noises. You have equipment noise. The treadmill itself is very noisy. Usually, often very loud ambient music. There is air conditioning, ventilation, conversations, etc., etc. So, using acoustics and some vibration is difficult, especially it's not attached to the person, it's attached to the treadmill. So, we're trying to pick out these footstep sounds effectively. And we can, the app can run on the smartphone or directly on the treadmills. So there are treadmills that allows you to run Android apps. And what we provide is something like real-time cadence measurements and then real-time ground contact measurements. So cadence, I guess, relatively speaking, is easier, but the ground contact time, which is the amount of time that your foot is contacting the ground, is much harder to do. And in this project, we had to do, in addition to placing the smartphone on the treadmill, we have another device that's positioned 50 centimeters away. This is where we do ground truth data collection. We use computer vision to process each of the foot, and this gives us ground truth. We also use a commercial solution called the RunScribe. So this is something you attach to your shoes. This is, I think, $500 kind of commercial device. And then we also use a traditional sport watch, right, to as a baseline comparison. So one more note, which is RunScribe is calibrated for each runner, where our device does not require any calibration phase. So we performed experiments with 61 valid subjects, multiple sessions, 363 running sessions, 40 hours of data, 24 treadmills in 13 public gyms, and comparing our solution against various baseline solutions. And just to introduce kind of our data processing pipeline a little bit, we start by measuring the sensor data, perform a running window, perform feature processing using things like mean variance normalization, because different people run at different kind of pace and different sound levels, denoising, acoustic features. We evaluated various acoustic features, MFCC, MEL, PSD, RMS. And in terms of the prediction and classification model, we also played around with a bunch of different ones, paying attention to which ones are energy efficient, right? Because we have to run this on a smartphone. What we end up with after performing all of these experiments is that a combination of MFCC plus mean squared error, root mean squared error, plus regression plus multi-layer perceptron actually provides the best result, right? This is in a multitask learning framework. So at output side, we also do some averaging and eventually produce the prediction that you can see on the smartphone end. We compare our system against smartwatch, and you can see that our error is about 2.9 steps per minute, which is much better than the smartwatch solution, which is about 10 steps per minute. RunScribe is better than us, but keep in mind that it's a $500 solution and needs to be calibrated. In terms of ground contact time, our system is has an error about 60 milliseconds, whereas RunScribe is about 90 milliseconds. So we're even better than a $500 commercial device. Okay, so I realize I'm going through these very quickly. I just want to sort of introduce as many projects as I can, but we'll hopefully have time for questions. So I kind of talked about these different projects in the physical health and fitness domain. Next, I want to talk about two projects in the emotional or mental health side. So the first one is a emotion glass platform. So this is this is something that's quite useful for a number of different applications. One is for patients suffering from depression, right? Instead of waiting for your next session with the doctor, this gives real-time in situ kind of alerts, right? And this can be kind of useful either as a direct feedback or even alerting your providers. It's also useful for commercial settings where business often want to know your emotional response in response to, let's say, a commercial or certain product placement. So this project, effectively, we designed this glass platform embedding IR camera and IR sensors, plus a couple other sensors. And we're using the eye and eyebrow shape as a feature to tell us what the apparent emotion is. In this case, we have to do essentially shape detection. We're also using motion vectors. So the way that you move your eyes or an eyebrow is a very strong indication of your emotion. And to be able to assess true data, true emotion, we are doing pupillometry, which is kind of how big your pupil is, especially in relation to the rest of the eye. So I'm going to skip most of the data processing pipeline, but just show you this comparison with a commercial solution. So the blue line is this thing called Tobii, which is a fairly expensive commercial device. Our solution essentially matches very well with this commercial device. And we are able to classify the 7 different emotions: angry, sad, surprised, fearful, disgusted, neutral, happy, with fairly good accuracy. So that, I think, maybe naturally kind of leads us to the final project I want to dive into some depth, which is AI therapist. So I think this is kind of exactly what this photo is showing, which is, can we somehow capture the expertise of therapists and combining with the recent advancements in large language models to enable these home devices such as Alexa, Google Home to act as a therapist. So we are very fortunate to be able to collaborate with licensed psychotherapists in this project. What they have told us is that, first of all, there are existing work related to this. We have research in emotion states, right? Our glasses is one of them. There's quite a bit of research in vital sign biomarker, human activity recognition. That's a lot of papers on that, as well as social interactions. But the most important thing that therapists do with their patients is essentially conversation, right? It's sitting down with the patients and asking certain questions and getting feedback from the patients. And this is exactly what this project is hoping to do. So the therapists they're not asking random questions, right? They are asking very relevant questions. And this is based on their training from years of training and also years of experiences. The two things that we are noting here are some of the medical kind of literature that we're also trying to incorporate, right? One is called the DSM-5, the other is the LA20. And what I want to emphasize here is that what most of the questions that therapists ask are trying to assess something called day-to-day functioning. And these day-to-day functioning, such as work, social relationships, self-care, is very much related to mental health. And that's also what our system is trying to do. And part of this project is not only to assess mental health, but also provide evidence-based psychotherapy. So there are two primary forms that we're incorporating, again, with the consultation from the psychiatrists. One is motivational interviewing. The other is something called cognitive behavior therapy. So the motivation of this project is that the access to mental health providers is it's very expensive often. They have limited bandwidth. And the third one is sometimes you have to rely on self-report, which is not often that accurate. So our system encompasses a couple of different components. One is we're taking advantage of LIM in part of this. The other is that we're using smart devices in home to give us even more objective measurements. So we're trying to provide pervasive, accessible, continuous, and effective mental kind of health care. So the first challenge is that there are infinite questions that one may ask, and they are not directly machine actionable. So working with psychiatrists, the first thing we did is to formalize these 37 dimensions of questions that can screen day-to-day functioning. Things like maintaining stable weight, managing mood, support from social network, doing access, and sports, right? These are these 37 dimensions where we draw questions from. And for each dimension, we would have 3 different scores. 0 is doing well, 1 is some issues, but nothing urgent, and 2 is require immediate attention. So we introduced our system, Katie, has a couple of components. One component is we're using sensors, right, to give us certain indications that a person potentially may not want to actually disclose. Well, things like, for example, we have alcohol sensors to know if to know about the alcohol consumption. But primarily, right, we are using Alexa, using Google Home to be able to converse with the user in a natural way and provide psychotherapeutic conversation interventions. And the way that we constructed our system is using using reinforcement learning to figure out what is the right question to ask. And we would start with the dimensions that real therapists would care about. Also, it's potentially dependent on the user's previous response. We would then get the response from the user, use LLM to parse the answer, and assess what is the dimension that the user responded for, and what is the score for that dimension. And for certain scores, such as if somebody scored a 2, which is the one that requires attention, we would also execute the psychotherapeutic conversation intervention, utilizing motivational interviewing as well as cognitive behavior therapy. So I'm skipping some of the details here. Just sort of very quick, kind of what the CBT does. First of all, it recognizes negative thoughts. It challenges the patient about these negative thoughts, and often reframing the thought in a different way helps the patient. So, so I'm going to skip some of these things, but the last part of this is that we also utilized home robotic vacuums as a platform where it can navigate to the location of the person to obtain more accurate data reading. As well as things like knowing whether the person has been moving a lot versus not much. So at the end of the day, right, we have a system utilizing reinforcement learning, natural language processing, and large language models to perform evidence-based psychotherapy. We start with dimension therapists care about, perform natural interactions, understanding what the user is saying, and providing personalized psychotherapeutic interventions. So we performed experiments over 14 days with 20 subjects, both in lab sessions as well as at home sessions. For 4 subjects, we actually have a very intensive 24-week of evaluation. And for them, we have bi-weekly therapist check-ins to evaluate how they're doing and make sure that the appropriate questions were asked, and also we obtained the feedback from the psychiatrists, and they're telling us that they do show improvements in anxiety, depression, and functional difficulties by using our system. So sorry, I kind of fly through many of these things. At the end, I want to just make sure to acknowledge my students who really did all the hard work, and our funding sources. So with that, I'm happy to take questions.
Hey, thank you so much for the impressive talk. Any question from the audience? Okay, maybe I can start off with the question. There's some echo. So in your work on house. So Mason, put your hands up.
Thanks so much for the presentation. I was wondering if you can speak to some end user feedback that you received and how that informed your design process across your projects.
So interesting. So yeah, I think there is a very kind of diverse range of projects, right? And some of these requires very frequent kind of sort of getting feedback from our user and potentially from a panel experts. For example, this one that I'm showing here, right? This is almost, it's very human-centric, requires us to not only talk to the therapist multiple times a week, and the design process for this project, for example, is very kind of, I think we spend many hours, many weeks to simply trying to figure out what are the 37 dimensions that we care about, right? This is, well, this is with the therapists, but with end users, obviously, we also have to get their feedback at the end so that we know what they feel about our system. So for certain projects, be able to update your design or even start from the beginning using feedback from clients, right, is very useful. I suppose for some projects, maybe I can go back to my first slide where we show kind of the range of different things. I guess for some projects, we do start with just our own kind of idea of how to design this. But at the end of the projects where we perform evaluations, there's typically, because it involves humans, so typically we have to get their feedback to be really know what the end-to-end kind of performance is. Hopefully that answers your question, but maybe not.
Yes. Thank you.
Simon? You need to unmute.
I think you are muted again. Or
can you hear me?
I think there's a little bit of echoing.
Sorry for the trouble, and thank you for the presentation. It's very exciting to see so many technologies that has a positive impact on this world. I have one question about the drone platform one. I noticed that they are primarily used in indoor environment. I wonder if you will see any potential or possibilities to apply such a drone platform in outdoor environment and possibly with other sensor modalities.
Great question. So it turns out, even though I only talked about the indoor one, our lab is working on both outdoor and indoor ones. One project I have not mentioned here is our outdoor drone, which is about this big because it needs to carry a rather heavy load. The focus of that drone is actually about carrying multispectral sensing. So it's using camera, LiDAR, infrared, and also millimeter wave sensor to perform various tasks. So I guess the quick answer is yes, we are looking at large drones. However, for the kind of tasks that we are focusing indoors, right? The sensor design and the way that it physically connects the sensors, that's quite different between the indoor version and outdoor version. I guess also largely because the application is quite different, right? For the outdoor, for example, you could imagine in agriculture type of setup, it will have to carry like something very different from, let's say, in a rescue recovery kind of scenario. But I think the architecture that we presented here, particularly the part where we use large language models, visual language models to comprehend what the task is, that can be used both indoor and outdoors, right? So much of this I do feel can be applied to outdoor setting.
Thank you for the answer.
Sure.
Vincenzo?
Hi there. Thank you very much. Very fascinating. Something caught my attention in the beginning about your augmented glasses and then prompting, let's say, keynote questions. Do you foresee this as like a training for those for social interactions, or maybe a replacement? I kind of envision AI suggestion and then response from another AI suggestion. Do you foresee anything like that? Let's say the keynote has this as well, and it's just that kind of conversation.
Yeah, I think you're asking whether this can be used to kind of train AI agents themselves, like
yeah, or is it going to disrupt like social interactions eventually?
Yeah. Well, that's a very interesting question. I guess when we were working on this project, we had a bunch of different kind of directions we could go with, right? One is targeting a particular set of population that are suffering from certain kind of social interaction kind of difficulties. We eventually settled on kind of targeting a wider population who simply wanted kind of help, right, to improve your kind of social interaction. But what you're saying, I think, is also interesting one, which is kind of using it as a way to even interact with other AI agents. Yeah, I guess I think this is still all relatively new, and we're trying to figure out what the what possibilities are. And I think the students would certainly love to explore various different directions.
Certainly, yeah. I see it, for example, replacing the therapist, and then maybe it could prescribe a drug or something for the AI therapist. Is that something you foresee, or no, it still needs to be interpreted by an actual clinician?
Well, okay, so that's okay. So this is actually where in Dr. House, this other project, right? We had to make sure to position it as, it's not, we're not yet trying to replace doctors, right? This is more of one we could use in training. The other is a kind of a triage kind of scenario where we can direct patients depending on how severe the symptoms are. But I feel like depending on our acceptance of AI technology and how much we can improve them in terms of removing hallucinations and all these other issues, we might see a future where much of the human kind of jobs are replaced, right, by them, right? Well, that's something that I think will happen at some point in the future, but we don't know.
Yeah, fascinating. Yeah, fascinating. Thank you so much.
Sure.
Asma?
Hi, Professor. Your work on AI-based drones for fall detection and the AI-powered mental health therapies is fascinating. I mean, I really like the idea. And given the sensitivity of health data involved in both applications, how do you ensure the strong data privacy or security measures?
So yeah, I think it's first of all, right? There is the basic things we need to do, which is the IRBs and making sure that we make it very clear what data is collected. I think maybe I didn't emphasize in the presentation, but the paper certainly make it very clear that we have these. We follow the typical procedures for this, right? Like informing what's the data, the consent we need from the users. So we have to make sure to do our due diligence to make sure all the right protocols are followed. And in terms of data security, right, we have to make sure these are encrypted, stored in a way that's compliant to the IRB's directives. So yeah, I think one is informing, one is consent, one is the data security. Yeah, I think, well, yeah, that's kind of making sure that we're compliant to the various things. I think at least our schools IRB they have a fairly strict kind of review process. So well, if you're compliant, then hopefully you're doing the right things. But you're right. I mean, our system involves a lot of kind of sensitive information. I think of the drone that's flying, collecting video data. Right now, if we release any of that data in any form, it needs to be anonymized. Has to be making sure that it's compliant. Right.
Yeah. Generally, we know like when it's involved the camera, the end users. Basically, we did also work on a fall detection detection systems. So, which actually is not involving camera, but when we did our primary research, we found like when it's camera involved, people are kind of they are not comfortable because they don't want to be seen. And when it comes also in terms of mental health data, there is always a stigma, right? So when it comes to mental health issues, so how did you handle those? I mean, when it comes to actual people to test the systems or involved.
So I want to maybe quickly kind of respond to the one with the fall detection. I think that's interesting design that we went with, which is instead of placing cameras everywhere that is continuously on, by design we are using more privacy aware sensors. That's so what we do is we put vibration sensors. So only when we sense something that resembles a falling do we put the drone out there. So the drone does have a camera, but it's not continuously taking images. It flies straight to where we estimate the falling location is, and then take a few photos to confirm that the person has fallen. Right. So by design, we are optimizing for a combination of things. That one of them could be the privacy.
Okay.
So yeah, we do consider the privacy in various phases of this, but it's definitely something that if you're doing anything this area, that needs to be part of the consideration. Yeah.
That's it. Thank you so much.
Sure.
Okay. I have a technical question and a non-technical one. So in your acoustic-based system for running metrics, in the title, I noticed you also estimate vital signs. I wonder if you can share a little bit of how that's done, because obviously the full body, upper body is moving. How you can estimate that reliably in the system?
Sorry, you said vital signs.
Yes, so you have in the title real-time vital signs and running metrics, but you did not touch upon the vital signs.
Oh, vital signs. That's a good question. I actually don't know the answer to that, because I was focusing on the running metrics. That's a good one. I may have to just ask my students about this part.
Okay.
Yeah, I actually,
because it's pretty challenging to do that when the body is in motion.
Right, and we are not putting any sensor on the body itself. So let me sort of go back to my students and to the paper to see exactly what vital sign means here. But that's a good catch. I actually just directly skipped that part.
Okay, no worries. Another small question is in a drone for indoor settings. Did you use some kind of visual SLAM to on the drone to locate the drone, or you actually utilize the camera, that overhead camera, to help with that?
So yeah, that's a good question. We did. Let me try to remember. We certainly thought about using Visual SLAM, but in order to do that, I think our drone was not able to. I forgot whether it was processing the data in a way that's more real time, or carrying a camera providing enough resolution to it. But in any case, we thought about using Visual SLAM, but at the end we had to use this over the bird's eye view camera to perform essentially the knowing exactly where the drone is and performing some of the navigation part. So that's kind of I guess a hack we had to do, right? But I think ideally we want to do some kind of visual SLAM or some kind of SLAM to make the navigation part more self-contained.
Okay, all right. Dylan?
Yes, thanks for that amazing talk. Lot of really cool projects, and that kind of leads me to my first question. I have kind of a general one and then a specific one. But from a general sense, the breadth of projects that you do is extremely impressive, and I wonder if you can comment on, holistically kind of managing that, because it's something that I always think about when you have different projects in different areas, and Mason commented on this a little bit in working with end users. But how does that work from just your own personal management of your lab across the diverse projects that you have?
So yeah, this is a I kind of want to say this was largely driven by sort of applications that pops up, and our students got interested in it, and then we decided to just dive into it. Almost saying that not as much of holistic planning as reacting to what is something that are exciting to our students. For example, the pill box, right? That's because one of the doctors in our medical center came to find us and ask us to provide them a way to address their problem. So part of this whole application-driven research is that we are reacting to needs brought to us. I think there is some merit to this approach, right? Because in that case, we know that we're working on something that's important. There are people who question kind of, how do you make sure you're doing fundamental research? And what we find is that when you are truly solving a problem that has not been solved, often in the process, fundamental research challenges arise. And that may be even sort of, I would say, better than some of the sort of challenges that you sort of sit in the lab and try to think up. But it is true that we are spread a bit thin in terms of often, you have a project with only one student kind of working on it. So that's something I'm also sort of trying to sort of struggle a little bit with, which is how can I identify certain, let's call it challenges and technologies across multiple applications, so that we can have students developing things that can be reused in multiple applications, right? So one example of that is maybe the pedestrian safety, construction safety, and acoustic intelligence one. These three are actually very much built on top of the same fundamental kind of idea, which is how to work with acoustic signals and how to make sense of that. So yeah, I mean, it is an application-driven research, but it is challenging to do, right?
Yeah, and just for clarity on that, I think it's amazing. I think like covering all those things is great, and having people come to you and addressing those questions. It's just, you know, thinking from your perspective, having to kind of manage all those students. I know I deal with that a little bit of different projects, and on a much smaller scale than this, and it's challenging. So I applaud you in the breadth of this. And then maybe one quick question. I think we're kind of getting on time here, but with respect to the running algorithm that you had with the audio side, we've been playing around with things for a number of different applications, and the variant scaling and the scaling of different users is a really, really important aspect of these from what we've found. But you also had the filtering in there, and I'm always curious on what your take is on filtering the data, and what level of filtering you're doing, because I've heard both sides of the coin when you're putting it into these deep learning models, that maybe you put in raw data or maybe you filter it. But what's your take on that?
Yeah, I think it's a debate, right? It's like is doing more better or worse, right? Like if you believe in this whole deep learning is able to really find the real features, you shouldn't do as much. I mean, but then there is also people do these convolutional neural networks, right? That's kind of also trying to apply expert knowledge to the images. So I think if you do not have enough data, then you should try to do as much kind of filter according to what you know about the application as possible. Deep learning really works well if you have really billions of or millions of images and data, right? And that's not the case for most of our projects. And I imagine for many of the human-driven research, unless you are using YouTube kind of data, any of the the heart sounds, for example, we're working on using heart sounds for diagnosing different types of murmurs, and we only have hundreds of recordings. That's not nearly enough to train something if you didn't have some kind of feature processing or expert knowledge, be able to encode expert knowledge. So yeah, I feel like you should utilize expert knowledge, especially if you don't have enough data.
Yeah, I think that's a great point, and very precise and actionable, as you said. In a lot of health applications, we're in the same boat, right? Where we don't have a lot. In some cases, we have a decent amount, I feel like, but it still pales in comparison to many other applications. So yeah, I think that's a great point. Thank you.
I'm aware that we are over time, but just one last question. For students who are starting in this area of research, do you have any advice, since you have such excellent track record of publishing in top venues? And I see like many of the projects actually requires a lot of efforts from the point of getting the research ethic approved to the point you collect data from 23 gyms. That's really a lot of work. Any advice for students?
So wow, it's a tough question. I'm have to think a little bit. Well, I think one thing I usually tell my students is that first of all, get your hands dirty and look at the raw data yourself as much as you can. I feel like a lot of a lot of people these days kind of just throw data into a network and expect everything to work out and potentially tune a couple of knobs without really paying more attention on the raw data. We kind of lost this when I was in school, right? When all of these neural networks were not popular. We had to look at the waveforms, we have to look at the data, we have to manually kind of understand many of the things. And that gave us, I think, intuition on how to design the system. And I just feel like nowadays I see class projects and everybody do the same thing, just throw them into a network and hope everything works. I mean, that's one advice, which is, try to understand the data better, the raw data better before just brute force kind of learning process. Yeah, I guess you have many great publications and students, so I think you know more about how to advise students. Maybe we can have exchange where we can kind of ask you to come to our lab and give our students advices. But yeah, I think it takes definitely time to think through how to do research, right?
Yeah, I think that's an excellent point. We cannot just assume that machine learning will magically work automatically. So that's something, go back to the data, visualizing, understanding are still important, and fundamentals in signal processing can be useful. Yeah, I really appreciate for the excellent talk and the Q&A after the presentation. So let's thank Dr. Jiang again. Okay, with some virtual applause.
Yeah.
All right, thanks everyone for attending.
Yeah. Thank you, Ron, for the invitation. Thank you all.
Okay, have
Thank
a
you
nice
so much.
day.
It was great. See ya.
Bye.
Bye-bye.
Be in touch.